And we're just using that knowledge now in mice to work on it in humans. And we're halfway there with PGCs, or primordial germ cells, but it's going to be tricky to go all the way to oocytes in humans. But I have no doubt that one day, just like in the mice, older women will be able to have eggs generated from their skin biopsy that will be useful for IVF, and in fact, they'll be young eggs. So first we do, this is the human study, first we do a skin biopsy on women with POI and azoospermic men, and we make stem cells. And I'll show you how it's very, very simple. So it's not a big deal, but any woman who has ovarian failure, we've done this up to 55 years of age, we just do a simple punch biopsy, not a big deal, and we put it in the appropriate media, and then it's been well shown, and Yamanaka got the Nobel Prize for this in 2012, that you can fairly easily convert those skin cells into a gigantic array of chromosomally and genetically normal stem cells. So we've done this experiment on 47 participants so far, 30 older women with no eggs, and 11 would be men with azoospermia, and 6 would be identical twin participants, which is a whole different fantastic story. But let me go through this as quickly as I can so that I don't overdo my time. And again, I'll be happy to show everyone more detail when we have more time. So the overall goals of this research project, we call it the CHOSE project, is to make competent germ cells that can make normal, healthy babies from simple skin cell biopsies. We can now make high-quality stem cells from skin biopsies and high-quality PGCs, primordial germ cells, from those stem cells. But the next big challenge is, we knew this from the mouse, we need fetal somatic ovary cells, or fetal granulosa cells, not adult granulosa cells. It has to be fetal, to incubate with those PGCs in order to complete the final step of making competent oocytes, and that really is the tricky part. So let me explain, when we're making oocytes from skin cells or from stem cells, all we're doing is recapitulating embryogenesis. So this is what the early epiblast cells look like in the developing embryo on day 11 or 12 in the human, and day 8 in the mouse. And all that in vitro gametogenesis is doing is copying this early embryonic process. I mean, you use transcription analysis at every stage of development, from the epiblast cells to the actual eggs or sperm, and you can do reverse transcriptase analysis. So you find out that way what are the genes that cause these particular cells to be converted into germ cells, and then you just use that in your culture media. So we're just recreating the normal fetal process, where these primordial germ cells then eventually at 3 weeks begin to transport themselves up to the dorsal ridge, where they're going to meet the fetal granulosa cells and become eggs. So this is just a very quick summary of an early paper showing, this is pretty amazing to me. The oldest we have, this is our first case report, 55-year-old woman, previously fertile, absolutely menopause for the last 5 years, generated young, mind you, young PGCs from 55-year-old skin cells. And the reason they're young is that we're just recapitulating normal embryogenesis. So think about this. Oocytes generated in vitro from iPS cells, that is stem cells derived from skin, will be very young. So think about it. In the future, a 38-year-old woman might be better off having a skin biopsy than an oocyte retrieval for IVF. So the Hayashi lab now can make fetal gonadal cells in mice, believe it or not, from stem cells, and produce healthy mouse pups just from skin cells with no need for the fetal granulosa cells. That's what we have to do to make this final step in the human. We have to be able to make human fetal gonadal cells, and that's what we're working on. If we can make competent human fetal granulosa cells from those stem cells in a different culture from the culture in which we make PGCs, then we can culture those PGCs in media with those granulosa cells, fetal granulosa cells we've also made from the stem cells, and then we should be able to get oocytes. So this is my colleague, I call him the X chromosome, Dr. Hayashi, and myself, I call me the Y chromosome. That's just for humor, of course, but we've worked together on this for a long time. And there we are at UCLA Stem Cell Center talking about our first human project in doing this. And there I am. That was my birthday 3 years ago. I spent in Kyushu, Japan, but I've been to Kyushu many times working with Dr. Yashi's team. And this is Amanda Clark, who is our major human connection, and she's the head of the stem cell program at UCLA. And so she is a crucial part of our collaboration. And there you can see with me and Dr. Hayashi, you can see Kyle Orwig, who's going to be focusing on the sperm side. In other words, I'll be doing the biopsies, and I am doing the biopsies. Amanda Clark is going to work on making oocytes, and Kyle is going to be working on making sperm. Sperm are going to be more difficult than oocytes. There we are at the UCLA Stem Cell Research Lab, and this is a moment when we inaugurated our program. So again, first one makes iPS cells from skin cells from the mouse's tail. And then the iPS cells are transformed to PGCs. And when you incubate those PGCs with fetal granulosa cells, in 3 weeks, you get competent oocytes. So that's what we're applying to the human at this point. And we have now discovered all the growth factors secreted by the mouse fetal granulosa cells so that fetal granulosa cells are no longer even needed in the mouse systems to make competent oocytes. But also we can convert these PGCs from our skin biopsies into iPS cells in a different system into fetal granulosa cells. So this was the first paper by Hayashi's group, Hakabi et al. Her name was Ori Hakabi, who did the lion's share of the work of actually reconstituting in vitro the entire cycle of mouse female germline from skin cells. There is Dr. Hayashi and Ori when we were together in their lab about to publish that first incredible paper that's just going to be changing our infertility world. So again, it all begins in the epiblast, where there's a certain number of cells that are specified to become PGCs. And all we have to do really is recreate that process in the embryo to make PGCs from our stem cells that we came from skin. And you notice something interesting. You have 3 different phases. In vivo, the primordial follicle is locked, and you can try as hard as you want to culture eggs from that primordial follicle in vivo, and you will not be successful. I mean, this has been an incredible amount of research, and nothing really is working very well because those primordial follicles are locked by the tissue pressure of the cortex. You can reduce that tissue pressure, and that helps a lot, but it's difficult. But in vitro, you can see that the PGCs are not locked, and they're just going to automatically develop and eventually become M2s. And so if the fetus didn't have a way of locking those primordial germ cells, then they'd be born without any eggs at all. So that's why the ovarian cortex and the locking of the primordial follicles and primordial follicle recruitment is so crucial. So there are 3 stages we call IVD, which is actually when the PGCs are developing their meiotic competence and becoming secondary follicles. And then there's IVG, which is gonadotropin-sensitive development of meiotic competence. And finally, IVM is just 1 or 2 days, where HCG or in vivo LH, it doesn't matter which, will allow that meiotically competent GV to develop into an M2 oocyte. We're just recreating what happens normally in vivo by doing it in the lab. And this is another visualization of it, showing that in the mouse, we have those 21 days where the actual primordial follicle, or what would have been a primordial follicle, the PGC, is entering meiosis, and eventually over those 21 days in the mouse develops into a primary follicle that is sensitive to gonadotropin. And then the IVG phase is where we incubate with gonadotropin for 11 to 14 days, just like in human ovary stimulation. And then it just takes 1 day for incubation in HCG for the final maturation to go from GV to metaphase 2. So these are just the genes we use. We can use 3 genes, but it's better to use all 4 originally described genes. You don't have to remember or memorize this. And we just mix the skin cells with these genes, and lo and behold, we get stem cells, embryonic type stem cells. Then you can maintain those embryonic type stem cells in just 3 genes. You don't need any feeder layers like in the early days of stem cells. And then you can you can incubate those in these 3 genes, next 3 genes, and you can make epiblast-like cells. And all these genes are commercially available. It's not a big deal to order them. Then the epiblast-like cells are incubated with 5 other genes, and behold, you have in vitro primordial germ cells. And these are the 5 commercially available genes needed to do this. And a simple outline of this shows you that then once you have the epiblast-like cells converted into PGCs, takes about 6 days of culture, then the PGCs can be mixed with fetal granulosa cells for 3 weeks, and then you get a competent primary oocyte, and then FSH culture for 11 days gives you GVs that are mitotically competent, and then HCG culture for just 1 day, IVM, gives you a mature oocyte. So it's no mystery anymore. So these are the cells, the stem cells that are incubated with granulosa cells to make PGCs. And we get secondary follicles. I'll go through this fairly quickly. And then we wind up with mature oocytes, and you can see these are mature oocytes. And they mature to M2 in just 1 day with HCG. And these are the first babies, mice, derived from the skin cell of the mother. So again, we're recreating the fetal process, so we get very young PGCs, and so even an old woman can give us young PGCs. But if the PGC, here's what's interesting, if iPS cells or stem cells are injected directly into fetal ovary without being at least 95% converted to PGCs, they will form a tumor. Stem cells form a tumor if they're not in a niche. They'll form a tumor rather than forming oocytes. But if they're injected into an adult ovary, they just die. So what the PGCs require are transcripts from the fetal granulosa cells, not adult granulosa cells. And we're now successfully making PGCs in humans, about to send this paper into Science, and we can get high quality PGCs in humans, just like we do in the mouse. But before we can make oocytes in humans clinically, we need fetal granulosa cells, and they need to be human. What about mouse fetal granulosa cells? Can we use mouse fetal granulosa cells to somehow or other mature these PGCs? And that study was tried by Yamashiro et al. Attempts to generate human oocytes by incubating human PGCs in mouse fetal granulosa cells. And he actually was able to develop cells that had oocyte-like qualities, but they weren't competent. They were not capable of meiosis, and they weren't competent. So in vitro produced gametes from skin to iPS cells to PGC-like cells in mice clearly generate fertile offspring. But human skin cells have also been influenced into PGC-like cells, opening the possibility for human in vitro gametogenesis. But here's the problem. It has to be species-specific. When human PGCs are incubated in mouse fetal granulosa cells, they make oocyte-like cells, but not competent human oocytes. Mouse ovaries do not provide proper signaling for meiotic entry of human oogonia. The addition of exogenous human signaling moieties or addition of reprogrammed human granulosa cells are needed. So that's what we think we can do now. This was a paper just published this year by Hamazaki in mice, and he was the lead author, but it was in Hayashi's group. And there's only 8 core genes. I mean, there are so many genes required to make an oocyte, but it's very much like SRY in the male. SRY doesn't make a testicle, but it's a trigger that allows all these downstream genes to make a testicle in the fetus. But it's the same way for these 8 core genes that make an oocyte. These are the genes, that's all you need to make an oocyte. That's it. But it's not because there's all that's required, but they are able to trigger the downstream genes that work to to finish the completion of the oocyte. So we call PPT8 the abbreviation for primordial to primary transition for primordial follicles. And if you want to culture those primordial follicles to oocytes, like people have tried, now all you have to do is incubate the primordial follicles in these 8 genes, and you'll get competent oocytes that make babies. But those primordial follicles really have more than PGCs in them. They have competent pre-oocytes in them. What if you just try to directly induce oocyte-like cells from the skin cells? We call that a dial. The PPT8 genes recruit primordial follicles to grow direct to secondary follicles ready to respond to gonadotropin. And they are all you need to unlock the primordial follicles. The primordial follicles realize have already gotten through the phenotypic granulosa cell stage. They have meiotic competence already and have undergone erasure of imprinting. So these 8 genes still don't solve the problem of how you convert stem cells or PGCs into oocytes. All you need is 8 core genes to grow and reach the IVG sensitive stage, but these oocytes are functionally competent to make normal offspring, but only if you start with resting follicles and primordial eggs. PP8 genes and granulosa cells are all you need to make competent oocytes that can result in offspring. But what about if all you have are stem cells? Well, then you need fetal granulosa cells. And how do you make and this is just a summary, so you can see that if a normal primordial follicle has already been exposed to granulosa cells, which it has, all you need are these 8 genes to make competent eggs. We can do that tomorrow. But what if you're starting from just a stem cell? Well, it's not going to make a competent oocyte. It'll make a oocyte, but it won't be competent because you still needed what the granulosa cells do. So, but now we can use these similar core genes to make granulosa cells and duplicate what the fetal granulosa cells secrete. And this was a paper by Yoshino, also in 2021 from Hayashi's group. And what they're able to do now finally is a much more complicated series of genes. You can now actually reconstitute follicle structures directly from stem cells, and you can make competent oocytes without the need for fetal granulosa cells, because we've already copied what fetal granulosa cells do. So I think my time is up, and you may not really be able to do all of this right now, but the point is, I'm sure in another 5 years we will be able to, or less, we'll be able to generate competent human oocytes from skin biopsies. But probably will not another 5 years or so, or 10 years of safety testing. So I'm not saying this will happen right away, but you can see from this paper of Yoshino that it's going to happen, because not only can we make PGCs from well-known genes, and not only can we convert primordial oocytes into meiotic competent oocytes with 8 core genes, but even now with a more complex group of genes and culturing, we can actually go directly from stem cell to fetal granulosa cell, or even from stem cell directly to competent oocyte. So that's the future, and it helped us understand how we can do IVM. IVM is so simple because the ovary's done most of the work for you already. And so thank you very much. I love Egypt, Egyptian Fertility Society. I can't wait till this COVID thing is over so we can all be together in person again. And thank you very much.
Okay, thank you.